What questions do you have? Things are going okay? I think we'll do a quiz on Thursday over 4.3 and 4.4. We're gonna get. We'll do a couple more problems here in 4.4 to get started, and then we will go into section 4.6 as well today, which talks about another method for finding a particular solution. So we did a little bit of that here with our non-homogeneous second order differential equations, but you can also apply it to higher order differential equations, of course. But the thing with the equations we've been working with so far, we've had constant coefficients on the function and the derivative on the derivatives. And so we're going to change that a little bit as what happens when you don't have constant functions on your as coefficients of your y's. And also when we talk about those forcing functions on the right-hand side, what happens if we can't recognize patterns for the derivatives? So that's how we're doing our guesses right now with our particular solutions is we recognize what the patterns of the derivatives have to be. And so that's what's making our guess be informed, right? Be educated. And so some of those we can't do. So we'll talk about another method today of how we can approach that. All right. So let's get back into this a little bit. I believe we stopped at number 16 last time with the last problem we did. So let's look at number 18. Like I said, we'll do a few more of these today. Make sure we understand what's going on, and then we'll get into some new stuff. All right, so number 18, we've got y double prime. So minus 2y prime, I can read, plus 2y equals e to the 2x times cosine x minus 3 sine x. So regardless of anything else, our first step for solving a non-homogeneous equation is to treat it like it's a homogeneous equation to start with, right? Because we're using that property that says that we can write the general solution to a non-homogeneous equation as the solution to the homogeneous plus a particular, right? So in order to be able to solve the associated homogeneous equation, what do we write down first? Yeah, our characteristic equation, which in this case will be m squared minus 2m plus 2 equals 0. Does that factor? No. Okay. Oh, it doesn't factor. So if it doesn't factor, we have to use quadratic. Good. So we'll get 2 plus or minus square root of 4 minus 8 all over 2. We plug into our quadratic formula. Looks like we're going to get a square root of negative 4 there on the end. Square root of negative 4 will be a 2i. And then we can cancel 2's, and it looks like we'll get a 1 plus or minus I here. Assuming I did my arithmetic correctly. Yeah. Okay. So what does your homogeneous piece of our puzzle here look like? Yep, there's an e to the x in there. What is the e to the x? What part is telling you the e to the x in there? The real part. Good. This part right here tells us that we've got an e to the x, right? And it's an e to the 1x. We literally use that number as our coefficient on the x. So yes, we definitely have an e to the x in there. Also have a c1 in there. Where does this part come in? Where does that I piece come in? Yeah, it'd be a cosine x, and then the second part will be a c2 It'll be an e to the, it'll still be a positive x because it's just that real number, but an e to the x, and then it'll be a sine x. Yep. Yep. Yeah. Get rid of that highlight there. There we go. All right. So again, remember this, the real part is your coefficient on the x in here, right? So it's a 1x. I can think of this as a 1 times I. And the imaginary part then here is your coefficient on your x in here. I'm not sure the arrows were helpful, but that's how we're getting the different pieces, right? The real part is the coefficient on the x in the exponential. The imaginary part is the coefficient on the x in your cosine and your sine. And the I doesn't factor in the solution. The I is just telling you you've got a cosine and a sine. Okay. All right. So far, so good? Okay. So now let's look at the form of our forcing function here, because this is what's going to tell us what our guess is for our particular solution. So notice that our forcing function has e to the x pieces and cosine pieces. So let's think about what that would look like if you take the derivative. If I take the derivative of, and don't worry about the coefficients, just think about an e to the x and a cosine x, an e to the x and a sine x. If I multiply e to the x times either cosine x or sine x, what pops up in the derivative? If I have a product there, what's going to pop up in the derivative? If I have e to the x times cosine or e to the x times sine, there should be two pieces that pop up. What's going to pop up? You'll get the function back, and you'll get the other piece, right? So you use your product rule, derivative of e to the x is itself, so you'll get the same function back again. But when I take the derivative of the second piece, I get kind of reverse, not really reverse, right? If I take derivative of cosine, I'll get a sine. Take the derivative of sine, I'll get a cosine. So I'll get both pieces, right? That makes sense? All right, so no matter what, the whole point of this is that no matter if I would have just seen this piece, or if I would have just seen this piece, I'd have the same guess for my particular solution as I would now that they're all together. Okay? What do you think the guess is going to be? Good, exactly right. I'm going to have an e to the 2x cosine x and an e to the 2x sine x. I'm going to have both of them in there, right? Because I don't know which one I need to start with, and I may start with some combination of the two. But both of those functions give me a derivative that's going to have an e to the 2x piece and a cosine piece, and an e to the 2x piece and a sine piece. Yes?
So if it were e to the 2x cosine, you put cosine and sine.
I always put the cosine and the sine. Yep. Either, and if I would have just had e to the x and sine x, I would have put both of them as well. Okay. Now there's one more part that's missing here. I haven't finished this off. Do I know how many of these I need and how many of these I need to start with? No. So what do I need to put in front of each of them? A constants, right? So usually we'll use an A and a B, and then keep going down the alphabet until we run out of letters. Hopefully you don't have a problem where you run out of letters of the alphabet. That would be bad. Okay. That's our guess. That's our initial guess, by the way. We may need to adjust it. But are we okay with how we got that? That part okay? All right. How do I know if I need to adjust it? Well, remember that, and we'll do another example here in a minute. Remember that if I see either of these in my homogeneous solution, then I'm going to need to multiply it by an x or an x squared or whatever I need to get rid of it, right? Or get it high enough. Because again, if this is a piece of my homogeneous system, try that again. If this is a piece of my homogeneous solution, then when I plug it into the equation, I'll get a 0, which doesn't help, right? right? Now, is this a piece of this? No. What's the difference between them? The 2x, right? That's different than this one. Okay, so I don't need to worry about adjusting it. If, and this is awful, but I'm not, need to erase that. If this had been a 2 right there, I would have had to adjust, right? Or vice versa, if this was just this 2 weren't here, I'd have to adjust. Okay. But now they don't match, so I don't have to worry about it. Okay. All right. So this is our guess. We don't have to do any adjusting. Any of the adjusting that you do is you just multiply by powers of x until you get out of the homogeneous solution. So it's not too big of a deal. It just makes your derivatives messy later. These derivatives are going to be messy enough. I'm glad we didn't have to adjust it. All right. So now our next step here is to differentiate. Both pieces require a product rule. But let's see if we can gather as we go. How am I going to note? Let's try the talk. We used this as our guess because I know that if I take a derivative of this, I'll either get the same thing back again, or I get something that looks like this, and vice versa with this one, right? Okay. So let's first think about if I take the derivative, what's going to give me this thing back again? Which piece do you differentiate to get an e to the 2x cosine 2x? Do I differentiate the first piece or the second piece? First, right? The derivative of that will be 2a times that piece, right? Because I'll have to take a derivative for the 2. Which piece do you differentiate on the second part, this part here, to get cosine? You differentiate the sign, right? And this will be a positive, right? So your coefficient there will be a 2a plus a b times e to the 2x cosine x. Because I can just factor it off. Right? Go through it again. If I differentiate e to the 2x, that leaves me at e to the 2x cosine 2x. The 2 pops out. That's where the 2a comes from. If I differentiate this piece, I need to differentiate the sign to get a cosine to pop out. I get b e to the 2x. It'll be a positive b e to the 2x cosine. Now let's do the other part. For the first term, I need to differentiate the cosine to make a sine pop out, right? What's your coefficient out in front going to be? Negative a, right? And then in the second part here, we need to differentiate the e to the 2x to make us e to the 2x sine x pop out. What's your coefficient going to be? 2b. Yeah, good. If you need to write it all out, that's fine. But remember, we're trying to gather coefficients when we're done. That's why I want to put them all together in the different pieces. I also really don't want to see 4 terms in that. Okay. All right. Let's do the same thing for the next part, because I got to do it again for the second derivative, right? Okay. So let's look at this piece. Pardon me. Same idea here. I want e to the 2x cosine x and e to the 2x sine x when I'm done. So let's just do each term individually. Here we would differentiate the e to the 2x, right? This one I will write out a little bit longhand. I'll give myself a little bit more room here. Oops, not red. I got to take the 2 through. So I'll have 4a plus 2b. And then the second piece, I just differentiate the sign and it gives me a cosine, right? So we'll get minus a plus 2b here. Do we see where those are coming from? I'm skipping a couple of steps, I know. But it's the same idea, right? These two here are coming from that one. These two here are coming from that one. All right, what's the next one look like?
-2a plus 4b.
Oh, you're doing which piece are you doing first? Sorry.
Oh, I did the sign.
Okay, that's fine. You flipped it on me. Okay, that's fine.
-2a.
Good. Okay, so Trace flip-flopped them around, right? This part is coming from this one. And this one is coming from that one. So in the first term, I have to differentiate the cosine to get a sine out, right? When I differentiate the cosine, a negative pops out. So I get -2a minus b for that one. In the second term, I need to differentiate the e to the 2x. A 2 pops out, and so that's where the -2a plus 4b comes from. I was trying to figure out where you got the 4 from the first term. Are we okay for where the derivatives came from? Let's simplify that a little bit. We get 3a plus 4b e to the 2x cosine x. And then we get a plus -4a plus 3b e to the 2x sine x. So far, so good? You can trust that you're not going to get one this ugly on the test, by the way. Okay. This is pretty ridiculous so far. All right. Let's see what we got, though. I need to plug that. Remember, I got to plug. The whole point of this is that this, when we plug in all of this stuff, when we plug it in up here, it has to work, right? So just to write that down, if we take yp double prime minus 2yp prime plus 2yp, that has to equal, I'm going to distribute this out, e to the 2x cosine x minus 3 e to the 2x sine 3x. When we plug it in, it has to work, right? That's the whole point of this. We're trying to find a solution to the equation, right? When we plug it in, it has to work. Okay? Let's gather coefficients now. So let's just do the same idea that we did before. I'm going to erase some of this stuff on here because it's going a little crazy. All right. Here's e to the 2x cosine x in the second derivative. Here it is in the first derivative. Here it is in the original function. Right? So when we take this minus 2 times this plus 2 times that, I have to get the coefficient out in front here, right? So just to write that down, when we take 3a plus 4b minus 2 times 2a plus b plus 2a, that has to equal 1. All right? Just underline it again. Here's the piece that's in the second derivative. Here's the piece that's in the first derivative. Here's the piece that's in the original function, right? So that minus 2 times that plus 2 times that has to equal that piece. Do we see it? Okay. You tell me the other equation then. I better have two equations. I have two unknowns, right? You tell me the other equation.
Plus 2 minus A plus 2B. Minus.
Oh, I see what you're saying. So it'd be minus 2 times negative A plus 2B. Okay.
And then plus 2B.
Good. Exactly. And what's that have to equal? Fantastic. Good. Exactly right. That piece that I just put a box around plus minus 2 times that piece plus 2 times that piece has to equal that piece. Cool. We're almost done. Woohoo! Again, there's not a lot of calculus involved in these problems, are there? Just differentiating your YP a couple of times. Everything else is algebra. All right, let's see here. 3 minus 4 is negative 1 plus 2. Gives me an A. 4 minus 2 gives me a minus 2B. That equals 1. Negative 4 plus 2 gives me a negative 2A. 3 minus 4 gives me negative 1 plus 2 gives me a positive 1B. So far, so good. This is not a bad system to solve. You can solve for one variable, plug it into the other, or just do elimination. I'm going to take 2 times the first equation and add down to get rid of the A's. Yeah, did I mess something up?
Isn't it supposed to be positive 2B? 4B minus 2B. Yeah, for the top one.
Oh, yeah, it is. Thanks. Yes. So I did mess up, is what you're telling me. That actually makes more sense that it was positive than negative from a structure standpoint, because the system's coming out of the e to the x cosine x and e to the x sine x. The sine p should be positives, and then the cosine should have one positive, one negative. So yes, I messed up. All right. I'm still going to do the same thing. I'm going to take 2 times the first one and add down. Okay. If I take 2 times the first equation and add down, we should get a 5b equals negative 1. If I take 2 times the first equation and add it to the second equation, I get 4b plus b and 2 minus 3. So b is negative 1/5, which makes your a 3/5 if you plug it into the other one. By the way, the 5 in the denominator is not a huge surprise. If I do 2 squared plus 1 squared, the coefficient on the x in the e and the coefficient on either the cosine and the sine, you do the sum of the squares, that should be your denominator every time. So if you have e to the ax cosine of bx, then you'd have an a squared plus b squared in the denominator. That should happen. So the 5 being in the denominator is not a huge surprise. No, not a huge surprise to me. Maybe just a shock to you, but it's just the way the patterns work out when you take the derivatives. Okay. All right, so now we're done. What does our general solution look like to the original equation? Yep, the whole thing.
C1 e to the x cosine x plus C2 e to the x sine x plus 3/5 e to the 2x cosine x plus or minus a fifth e to the 2x sine x.
Good. Yep. Homogeneous plus particular. We found the coefficients for the particular. Plug it in. We're done. Yes.
Is that gonna assign 3x this whole time?
Oh, oops. Nope. Sure hasn't. Where'd you see a 3?
If that was assigned 3x.
Oh, God, it'd be a mess.
Do you have to do cosine x, sine x, cosine 3x, sine 3x?
Mm-hmm.
Oh, okay.
Yep, sure would. Yeah, if one of them had been a cosine x, the other been a sine 3x, yes, we would have had 4 pieces to keep track of, which means we would have had 4 equations and 4 unknowns. Which, yeah, we didn't want that. So I said, where was there a 3? I wrote the 3 because we had the 3 in front of it for the coefficient. I just spazzed and wrote it. All right. The process okay? I know the algebra is not necessarily the nicest thing, but the process okay? Okay. Like I mentioned before, if this had matched, this 2 right here had matched this, then you would have had to multiply everything by an x. Okay. So let's do something that looks like that, but not for one that's that bad, hopefully. We'll find out when we write it down. This is number 20. Y double prime plus 2y prime minus 24y equals 16 minus x plus 2 e to the 4x. That's a 16. It looks like a 10, maybe. I don't know. I don't think it really matters. Whatever numbers they put in for these problems, they don't tend to come out nicely anyway. So I don't think it matters whether it's 10 or 16. I guess you'll get some.
That's an equal.
Yes, that is an equal. Yep, yep. All right. No, it's fine. Make sure. Absolutely. My handwriting is terrible. Let's make sure it's perfectly fine. All right. First step. The characteristic. The characteristic equation is m squared plus 2m minus 24 equals 0. Is that a factor? Yeah, what's a factor as?
M is 4.
M.
M minus 4. M plus 6.
Okay. And so then you said it's 4 or negative 6. I agree. Cool. Homogeneous solution. Solution to the associated homogeneous equation. Why can I not talk today?
C1 e to the 4x plus C2 e to the negative 6x.
That okay? All right, so let's go look at this part. Notice it's in 2 different pieces. So let's say first, this part wasn't here. What would your guess be for the particular solution? Yeah, a constant, right? You got a constant at the end. My guess would be a constant, right? So that should be a part of it. And again, this is a guess. Should be a constant. I'll just call it A. Okay. Now let's say that this part wasn't here. What would your guess be? Let's make it even a little bit easier. Let's say that this whole thing weren't here. It's just up to there. What would your guess be? Yeah, be e to the 4x, right? If this part weren't here, and this part weren't here, so both of those parts, what would your guess be? yeah, a cx e to the 4x, right? Okay. So putting all that together, we probably should have something that looks like a bx e to the, well, let's write it this way. We'll write it as bx plus c times e to the 4x. That's just putting the two pieces together, right? Notice I didn't just use, even though when you differentiate an x e to the 4x, you'll get a constant e to the 4x out. I didn't just put a bx e to the 4x, I needed this constant piece too, because if I differentiate, I don't know that my b is going to match in both of those places, right? I might need something else to adjust it. Okay. So I really do need an arbitrary bx plus some arbitrary c to start with. All right. Pardon me. Are we okay with the guess? Okay. Now let's adjust, because I think I have to adjust something. Notice that this part here is the same as that part there. Right? Do you think I want to adjust just by putting an x right here? Does that make any sense? No, because then I would just wrote b plus cx, right? That doesn't make any sense. So if I'm going to adjust, I need to adjust an x here. I don't need it on the a, because the a had nothing to do with the e to the 4x, right? That 16 is all by itself. I don't need to worry about the 16, but I do need to worry about the x plus 2 times e to the 4x. I will write it this way, though, just to help with derivatives. I'll write this as bx squared plus cx e to the 4x. So I'm going to emphasize just one more time, because there's a little bit of stuff going on here, right? Since I have some arbitrary-ish polynomial multiplied by the e to the 4x, I need to have an arbitrary polynomial as my coefficient times e to the 4x. Okay? I can't just do x times e to the 4x there. I have to have something times x plus a constant times e to the 4x. Okay? Even if this 2 hadn't have been there, I would have needed the same thing. Okay? Then I need some canceling things, some stuff to cancel out. All right? So I have to be a little bit careful with that. And then also, I need to take this adjustment x and multiply it all the way through because of this e to the 4x that popped up in the homogeneous part. I've got to adjust both of those things. We see where that came from? It's an important piece, right? Okay. So let's see if we can go through this mess. I need first and second derivatives. Good news is the a goes away after the first derivative. As a matter of fact, the a is pretty easy to figure out what it has to be anyway. But we'll leave it there for the time being because it needs to be there. All right. First derivative then, I'll do my product rule. You'll have a 2xb plus c e to the 4x, and then plus a 4bx squared plus cx e to the 4x. Just doing product rule on that. Both pieces have it, just to help with the second derivative. Let's just do a little bit of algebra simplifying here. Both pieces have an e to the 4x in them, right? We'll have a bx squared, certainly here. Oops, no we won't. We'll have a 4bx squared. And then on the x, I've got a 2b and a 4c, right? And then plus a c. only gathered everything because I thought it made it a little easier to take the second derivative. Because now product rule again, here we'll get 8bx plus 2b plus 4c, e to the 4x, and then plus 4 times 4bx squared 2b plus 4cx plus c e to the 4x. Let's simplify it a little bit. It was 16bx squared, right? I've got how many x's here? I've got 8b here and another 8b there. So we have a 16b. And then for c's, we've got what? 16c x. And then 8c on the end. Is there a 2? Oh, there is a 2b in there. Thanks. I said 8c, didn't I? I wrote 4. Thanks. All right. Now let's see if I made any other errors as we go along here. Go back through my derivatives because it's easy to do, clearly. 4bx squared, 2, and a 4, and a c. And then the next one is 8, and that. And then just rewrite it. A 4 instead of 16, and an 8, and a 8 is a 16, and a 16. Okay, looks like I'm okay. All right. Whew, that was fun. Let's see if we can put it all together. Remember, again, we're just trying to get our pieces to match, right? Okay. All right. So let's go through all of this mess and make sure our coefficients all match. So first, like I said, I don't think it's too hard to figure out what the A has to be. Because when I differentiated this A, it went away in the next two pieces, right? So it's not here and it's not here. The only part is it's right here, isn't it? The equation we get is negative 24A equals 16. Right? Yeah? Okay. So that part, like I said, is not too hard to figure out. What do we get? Negative 2/3 for A. All right, so let's see if we can figure out what the other two equations have to be. Well, good news is that I think one of the other equations is going to be pretty straightforward as well, perhaps. Notice that each of these things has an x squared and x, and it's some sort of a constant term in it, isn't it? But let's look at the x squareds. There's just a b there, right? There is no c on that x squared. There's no c on that x squared. There's no c on that x squared. So what does that tell you the b has to be? Because again, it has to equal the right-hand side here, right? So what does a b have to be? It's just be 0, doesn't it? Because there are no x squareds on the right-hand side, right? So our b here has to be 0 because there aren't any x squareds. Which makes the rest of this go pretty quickly, hopefully. Either that or we've got something incorrect somewhere along the way. Well, let's see if things match up here. All right, let's do... See if we can match up x terms. Start there. And then we'll see if make sure the constant piece matches. Hope it does. Otherwise, I made an error somewhere. Here's an x term. What does that x term get multiplied by? The negative 24, because it's in that part, right? Okay. So I certainly got a negative 24c. Right? Yep. Okay. Here's the x part here. But we already know the b had to be 0. So this part, what does that 4c get multiplied by? 2. So we should have an 8c. And then, oh, shoot. And I knew something was wrong. Because the other piece here is going to be that 16c, isn't it? And everything's going to cancel out. And well, that's okay. I mean, that's okay. Because this would all, if I look at this last term, you get a 16c. That had to be, ooh. That would have had to be negative 1. So something is not right. Okay, what did I do wrong? What did we do wrong along here? What did I do wrong? Okay, yeah. I'm just looking at another problem in here. I was like, I did exactly what that was doing. Anybody else see where it went wrong here? What happened here? This is the right guess. You know, it shouldn't matter. I'm sitting here thinking, well, we'll make an error here with the guess, but even if I think about distributing this to here and to here, I still would have had a similar type of guess, and I would still had a constant times e to the 4x and just a constant times e to the 4x. So there's no point in splitting it into 2. I still need to adjust it by the x. I don't see where I made an error in my derivative. What's that?
Is it the b equals 0 because the x squareds cancel?
Did they all cancel?
Where we don't know that b equals 0 since the x squareds cancel is asking. Because you have 16bx squared added to.
Oh, they do cancel. Thank you. Holy cow. Thank you. That's much better. I appreciate that. I knew something was going on. All right. So like Marcus said here, thank you. I was trying to have a hard time figuring that out. All right. Here's 16bx squared here, right? I was not careful. You got to be careful. Be careful. Me, talking to me. There's a 16. 2 times this gives me 8 more. There's 24. Minus 24. They just cancel. That b, I don't know anything from that. That was the issue. Thank you, Marcus. Bailed my butt out. Appreciate it. All right. So let's go back to this. Great. Phew. I knew I was doing it. I knew I had it set up correctly. Here's the moral of the story. Actually go through the algebra instead of assuming what was going on. That was what I did, right? I didn't see any other x squareds in there. And so, that has to be 0. And then I knew something was going to be wrong at the end. All right. Okay. Let's go through the constants now. This should work out better. We've got 2b plus 8c, because now I don't know what the b is. They literally canceled out for the x squared terms. I'm going to go with, okay, I do need, I was doing the constants. Let's go back. Here are the x's. Sorry, I started with the constants. Here are the x's. We've got 16b plus 16c, right? Here are the x's here. I've got to multiply that by 2. And then here's the x here. We'll have minus 24c, and that has to equal negative 1. Let's go through that again since I messed up earlier and I'm a little bit flustered. Let's go back to this here and make sure I didn't do anything. Here is the x term that's in the second derivative. Here is the x term that's in the first derivative. Here is the x term that's in the original function. So 16b plus 16c plus 2 times 2b plus 4c plus c, minus 24c. Okay. Now let's do the constant part. 2b plus 8c. And then I'm looking at the wrong one. Plus a c. Not a plus a c, plus a 2c. Because I got to multiply by 2 for the derivative. 2b plus 8c, constant part in the second derivative. There's just a c as the constant part in the first derivative, but I got to multiply that by 2. There is no constant part here. What does that have to equal? Negative 2, good. That's this part up here. I apologize. Again, thank you, Marcus. Appreciate that a lot. All right, let's see if we can finish this off, because I'm sick of this problem already. 16 plus 4 is 20b. I'm now really nervous that I'm doing my arithmetic right. 16 plus 8 is, the c's cancel. That's nice. 16 plus 8 is 24 minus 24. That is helpful. So we get 20b equals negative 1. And this is just 2b plus 10c equals negative 2. All right, so we get b is negative 1 over 20. That gives me negative 1/10. When I put that in here, that gives me negative 1/10 here. Add it to the other side, I get negative 19/10. Divide by 10, I get negative 19 over 100. And now we can put everything together. Finally. So your original homogeneous equation was solution was C1e to the 4x plus C2e to the negative 6x. And then we put the rest of the pieces in here with our guess. Minus 2/3. I'm going to factor out the minus since they're both minuses. Minus 1/20th x squared plus 19 over 100 x e to the 4x. That was just going back and putting it back in our guess. See, we can mess up. I can mess up too. It's easy. What are you supposed to do when I mess up like that, by the way? Yeah. Oh, that was pathetic. But that was boo. That was definitely boo worthy. Holy cow. All right. Let's do one more since that one went so well. See if we can do another one. All right. Let's see if we can put one in here with an initial condition. How does that sound? Why not? Let's just add to the mess. This is number 28. Hopefully this is not so bad. 2y double prime plus 3y prime minus 2y equals 14x squared minus 4x minus 11. And we're going to say y of 0 is the same as y prime of 0 is 0. First step. Good. Yeah, characteristic equation, which is what? Good. How does that factor? Good. Agree. So your roots are negative 2 and 1/2. So what's your homogeneous solution look like? Good. That okay? Looking at the right-hand side of the equation, what's your guess? It's it looks like a quadratic, right? So it should be some ax squared plus bx plus c. Do we need to adjust that quadratic based off of your homogeneous solution? No. No adjustment is necessary. If you had m equal to 0 for one of your solutions where you would have had a c1 all by itself, would you have had to make an adjustment? Yes, you would have had to multiply by x, right? Okay. Oh, good. We have a quadratic. This shouldn't be so bad to differentiate, I hope. First derivative. Good. Second derivative. Good. That's harder for me to mess up. Not impossible, but harder for me to mess up. All right, so let's start getting our equations. Remember, we're going to do 2 times that one plus 3 times that one minus 2 times that one, right? And then we got to equate coefficients on both sides. Let's do x squareds first, because I think that's easiest. If you look at your x squared terms, what equation do you get? You got a minus 2ax squared up here, right? So just get a minus 2a is the coefficient on the left. What's the coefficient on the right? 14. Good. That made life easy.
Why is it negative?
Because of the minus here.
Oh.
Good question, but it's a negative because of that minus. Yep. So a is negative 7. Let's do your x terms. What's the coefficient on the x on the left-hand side?
6a minus 2b.
Good. And on the right-hand side, it's negative 4. I know that a is negative 7, so I get negative 42 here if I plug it in. But I'll add it to the other side, so I'll get 38. Divide by negative 2. So we should get b is negative 19. Assuming my arithmetic is correct. What's the constant on the left-hand side?
4a plus 3b minus 2c.
Good. And on the right-hand side, it's negative 11. Okay. Negative 28 minus 57 is what? Negative 65. Add to the other side, we get a positive 54. Divide by negative 2, I think I get negative 27. Of course, the way that today is going, I would not quote me on that. Are we okay with where the equations came from? Any questions on where those equations came from at all? Okay. So, if we're just to write down the general solution, we have our c1 e to the negative 2x plus c2 e to the x over 2 minus 7x squared minus 19x minus 27. That's our general solution, right? That was much nicer than the previous problem. Now we're ready to use our initial conditions to figure out what C1 and C2 are. Before I do that, let's differentiate and then get our equations. If we take the derivative here, we'll get negative 2c1 e to the negative 2x plus 1/2 c2 e to the x over 2 minus 14x minus 19. Using our initial conditions now, which at least they gave us some nice numbers to work with in this particular problem. I plug in 0 for x, we're supposed to get 0 out for y in both the function and the derivative. What do you get when you put 0 into the original function? That's the derivative, but yeah, I'll do that one. Negative 2c1 plus 1/2 c2. There's another piece on that. Minus 19. That's supposed to equal 0. Got all choked up about it. Original function, what do you get? Yep, minus 27 equals 0. Good. There's our two equations and two unknowns. Like before, let's multiply the first equation by 2 and add down. You should get 5/2 C2. Oh, what is it? Now they have to give us nasty numbers again. Minus 73 equals 0. 2 times 27 is 54 plus 19. So this tells us C2 is positive 146 over 5. Yeah. Okay. C1. Oh, goodness. 27 times 5 is what? 135? Subtract 135 from that, I get 11? Is that right? Negative 11? Yeah, okay. So I should get 11 over 5 when I move to the other side? Is that right? Or did I do it backward? Okay, so it's negative on the other side. Okay. All right. In any event, there's our constants. So finally, we're all done with this mess. You get negative 11 over 5 e to the negative 2x plus 146 over 5 e to the x over 2 minus 7x squared minus 19x minus 27. You know, it's not that hard to make numbers to come out nicely. You don't have to have all these nasty fractions. You know what you do? You start with the answer. Then you do that. Okay. I get kind of grumpy about it. It's not hard to make the number come out nice. Are we okay with the process? All right. We beat this to death for a couple of times. Let's do something new for the last 15 minutes. All right. So I mentioned at the beginning of class that this process works nicely if we have equations that have constant coefficients on the y's, and if we have nice forcing functions that behave nicely as far as derivatives go, right? But what if we come across something that looks like, this is number 2 in section 4.6. So section 4.6, the title of the section is Variation of Parameters. And number 2 in this section asks us to solve y double prime plus y equals tangent of x. Okay, so far they haven't done anything nasty to us as far as changing the coefficients into something different, right? There's still constant coefficients, but they have changed the forcing function because our tangent doesn't have nice patterns for the derivatives, right? The functions that we've dealt with so far have nice patterns for the derivatives. Either it's e to a power, so that just pops back up again, or a power of x times e to a power, that piece pops back up again, or lower powers of x. E to the x and cosine and sine have a nice pattern, right? All those things have nice patterns. Tangent doesn't. Okay. So there must be some other way to attack this. Well, we're going to attack it in the same fashion that we've done before. We're still going to find homogeneous solution plus particular solution, right? Homogeneous solution is the same thing we've done all along. Find your characteristic equation. In this case, it's m squared plus 1 equals 0. We get plus or minus I for our roots. So then our homogeneous solution looks like C1 cosine x plus C2 sine x. The imaginary part is 1, the real part is 0. That is same concept. Exactly the same concept we've done before, right? That's not new. The new part is how do we handle this? Right? Now, can our particular solution be a constant times C1 plus constant times, try that again. A constant times cosine plus a constant times sine? No, because that's our homogeneous part, right? So if we think about it as a quote unquote linear combination, I can't use constants times each of those things, right? So this is why it's called variation of the parameters. Here are some parameters. Typically we think of the parameters as being constant. Instead of thinking of them as being constants, we're going to think of them as being functions of x. Okay? So let's do this in more general terms so that we get a formula that we can use all the time to help us figure out what the particular solution is. So we're going to assume our particular solution looks like y sub p equals u1 y1 plus u2 y2, where u1 and u2 are non-constant functions of x. We've got parameters C1 and C2. We're going to vary them. That's variation of parameters. That's why it gets its name. Rather than thinking of them as constants, we're going to think of them as functions of x that vary. Okay? Very clever name, right? All right. So, again, I'm going to do this in general so that we can come up with a formula, because you're never going to want to do this every single time. You're going to want to come up with a general formula. Okay? All right. So, let's start with the equation. Let's say we have y double prime plus py prime plus qy equals some f of x on the right-hand side. Okay. Again, the idea here is that, oh, by the way, notice that we've divided out any coefficient that's on the y double prime piece. Okay? Just to put it kind of in that normal form, if we will. Right? Making the coefficient on the y double prime the highest degree term a 1. Highest order term 1. All right. Again, particular solution has to work, right? So when I do the second derivative here, first derivative here, original function here, it has to work. Okay? So, pardon me, goodness. All right, so let's look at what happens when we take this the first derivative. I'll just do this. Let's write it this way. Certainly, if I plug the original function in there, I multiply it by the q, right? That's just putting the original function in. I'm going to work right to left. Okay? I'll probably do, well, I'll stack it. I got to put the first derivative in here for my p, don't I? So the first derivative here will be a u1 prime y1 plus u1 y1 prime. That's product rule, right? And you got to do the exact same thing for the second one. Now I got to take the derivative of both of those things, don't I? So u1 double prime y1 plus u1 prime y1 prime plus u1 prime y1 prime. Goodness, lots of stuff. Plus u1 y double prime. That's just the second derivative of the y, the ones. Let's do the same thing with the 2's. It's the same exact formulation here. Just with the y2's. I know I'm going a little quickly, but I only have about 4 minutes left, so just trying to get through it. All right, so we're going to break this up into pieces. Notice that, let's do this first. This part here that I'm underlining, all the parts that I'm underlining in red, all have no derivatives on the u's, right? We agree? So in those red pieces, and I'm going to write them off into the red here. All those, sorry, try this again. Every one of those pieces, I can factor off a U1 or a U2, depending on which one I'm looking at, right? So one of the pieces I'll have is a U1 times Y1 double prime plus PY1 prime plus QY1. And I'll have a U2 and then with the Y2's. Any thoughts on why I wrote that in red? They go away. Why do they go away? What are Y1 and Y2 assumed to be? Solutions to the homogeneous equation, right? That looks like I've plugged it into the homogeneous equation, right? So both of these pieces end up being 0. So this piece, this piece, this piece, this piece, this piece all go away. Notice in particular the Q part goes away, doesn't it? Yeah? Okay. So we're going to divide the next pieces into, I'm going to do this quickly and you can check my algebra later. I'm going to divide this into a couple of different pieces for the rest of what's going on here. Part of it is going to be a derivative of a U1 prime Y1 plus a U2 prime Y2. Another part is going to be P times what looks exactly the same thing. Except it's not in the derivative. You can see part of this. Here's part of it here. That's the derivative of U1 prime Y1. And that's the derivative of U1 prime Y1. Or U2 prime Y2. Right there. Okay. And then I see the exact same part here. Here's a U1 and a U2 that part there. Okay. The last piece that's left over here is, should I write the right thing down? U1 prime Y1 prime plus U2 prime Y2 prime. That's all that's left over. That's all that's left over when you simplify all that stuff. Okay? All right. Why is this helpful? Well, we're going to make an assumption on these things, and then we'll finish this off on Thursday. These two things are exactly the same, right? It'd be nice if they just go away. So that's what we're going to do. We're going to assume that U1 prime Y1 plus U2 prime Y2 is equal to 0. Okay? That makes our other equation mean that U1 prime Y1 prime plus U2 prime Y2 prime has to equal the f of x on the right-hand side. This gives us a system of equations to solve. We're going to solve this system of equations for u1 prime and u2 prime. This is a system of equations. It's functions, but it's a system of equations in u1 prime and u2 prime. So we're going to use those equations to help us solve this equation, or the system to help us solve the differential equation. Okay? We'll do that on Thursday. Also, remember, we'll have a quiz on Thursday over 4.3 and 4.4. There'll be 2 problems. One out of 4.3 and one out of 4.4. Okay? Do that on Thursday. We'll finish this up and we'll do examples of this on Thursday as well, and this will just be what we do on Thursday. All right? Have a good one. We'll see you then. I apologize for the error, and thank you again, Marcus. I appreciate you helping me out.